Now, I will start talking about a little bit about the structure of algebraic groups over Q, semisimple algebraic groups over Q, which I started on last time I said something, but let me do it over again, some of the things. Oh, well, let me get down to the Margulis theorem told us that any lattice, in a irreducible lattice in a group of R rank greater than or equal to 2 is necessarily arithmetic. It's an arithmetic subgroup of an algebraic group. What does that mean? First of all, it's essentially it's something like this. You have a subgroup of SL and R, which is also a set of zeros of a bunch of polynomials, all defined over Q in the matrix entries. And it's a group in its own right, subgroup of SL and R with this property. I will usually take only real point, consider only real points as the algebraic group. I wouldn't bother about the complex points. Though correctly, one should really call the algebraic group the complex points. I will also call the real points, and I will also call any subgroup of finite index in the real points also an algebraic group. In particular, the identity connected component of the set of zeros of a bunch of polynomials, which is an algebraic group, is also considered as an algebraic group over R. So by an R algebraic group, I mean something which is a subgroup of SL and R, which is also the set of, which is a finite index in the set of zeros of a bunch of polynomials on M and R with coefficients in R. If it has coefficients in some other field inside R, I will call it an algebraic group over that field. For example, algebraic group over Q means that these polynomials have to have their coefficients over Q. Okay, now, and for such a group G, the integral points, that is G intersection SL and Z, is a fairly large group, at least when G has some simple necessary property. That is, the condition is that G should have no characters defined over Q. It has no homomorphisms into the diagonal group, which is a polynomial defined over Q, which is the restriction of a polynomial in M and R to G, which with the polynomial having all its coefficients in Q. So if the group does not have any characters defined over Q, then one knows that GR by GZ has finite measure. That's a theorem of Borel and Harishchandra. They also gave a criterion of when GR by GZ is compact. Not every finite measure space, homogeneous finite measure space is necessarily compact. It is compact under certain strict conditions. Namely, the condition is that it should not admit, the G should not admit any subgroup which is connected and diagonalizable over Q. That is, should not admit a subgroup T which has a conjugate in diagonal matrices in SL and R under an element of SL and Q. That's the condition for the group, for the quotient group to be compact, not quotient group, quotient set G mod gamma to be compact. Okay, now once one has this subgroup T, which is called subgroup T is called a split torus. If it's an algebraic subgroup, T is called a split torus over R. If it has a conjugate in diagonal matrices over R, it's split over Q if it has a conjugate inside the conjugate by an element of GL and Q into diagonal matrices. So T has a conjugate in diagonal matrices by a conjugation which takes by an element in GL and Q. Then you call T a maximal Q split. You call it a Q split torus, and if it's maximal among them, fix a maximal Q split torus, and let us denote by Z T the centralizer of T in G. Under the adjoint action of T consists entirely of after conjugation, it consists of diagonal matrices, as I said. So under the adjoint action of T, the Lie algebra will decompose into eigenspaces for T. There will be the trivial eigenspace, which is denoted Gothic ZT, which is the Lie algebra of the centralized ZT of T, the direct sum with a number of other eigenspaces. That should be small phi there, small phi there. Unfortunately, I have not corrected it. In fact, I rewrote some of the things, but didn't have time to make the proper corrections. So G is the direct sum of ZT and direct sum phi over phi, small phi over capital phi of eigenspaces G superscript small phi. Then capital phi is a set of non-trivial characters on T, which occur as eigen characters for T acting on the Lie algebra. That set phi is called the Q roots of G. I will not, in the sequel, I will always simply say root, not Q root. I mean a Q root, but I will say root. It's a, as I said, it's a non-trivial eigen character on T. Okay. The centralizer of T in G, in the Lie algebra G is denoted ZT here, and that is the Lie algebra of the group centralizer ZT of capital T in G. One introduces an order on XT, which is small to Z power R. So you choose a basis and you write any element as a linear combination of basic elements, sigma AI. It's an ordered basis. And so you say that an element in XT is greater than 0 if the first non-vanishing AI is greater than 0. And so XT is an abelian group, free abelian group on R generators, where R is called the Q rank of G, and it's also the dimension of T as a Lie group. The character group T is called XT. And let me denote by phi plus set of all small phi in phi, capital phi, with phi greater than 0 in this lexicographic order. Once you have that lexicographic order, there is a unique subset delta in phi, such that every root alpha, every root phi in phi is a linear combination of elements of delta. So in particular, delta will be a basis for XT. Every element, sorry, delta may not be a basis. Delta will be a linearly independent set inside over Z inside XT, and every root in phi can be written as a linear combination of elements of delta with all coefficients of the same sign, either all non-negative or all non-positive. So delta is called the system of simple roots of G with respect to T. As I said, I won't say Q roots, though I mean Q roots all the time. And the number of elements in delta is actually equal to the rank of the free abelian group. So delta is a basis of, if you like, of XT tensor Q. It may not be a basis of XT over Z, but it's certainly a basis of XT tensor Q over Q. So for root alpha, this subspace sigma K alpha in phi GK alpha, that is, you take all the eigenspaces corresponding to multiples of alpha. That is turns out is the nilpotent Lie algebra. It's easy to see. The bracket of GK alpha and GL alpha will be K plus L alpha, so long as K is positive. I'm sorry, I made a mistake here. I have not said that. K alpha with K positive. For a root alpha, this is, I only take positive multiples of alpha. Actually, one need to take only integral multiples of alpha. And then this is the nilpotent Lie algebra. We denote the corresponding Lie group, U capital alpha. Lie algebra itself will be denoted by German Gothic U with superscript alpha. No, maybe not superscript alpha, but subscript alpha. This should have also been subscript. We'll see. The direct sum U of the G phi has also P, which is the direct sum of, which is this part U. U is all those sum of all the eigenspaces G phi, which correspond to all alpha and phi plus. And then to add on to that ZT, the centralizer of T. This is a Lie subalgebra, as is well known and one can see easily. And it turns out that the corresponding Lie group U and P are Q algebraic subgroups of capital P, which is the semidirect product of ZT and U. Okay, this part this ZT is the Lie algebra of ZT, and this is the Lie algebra of U, and ZT times U has this as the this plus this as the Lie algebra. Now, one has the notion of what are called Q parabolic groups. And once again, I'll say parabolic without saying Q parabolic. So fix as theta and delta, and denote by phi subscript theta, capital theta and delta. Like phi subscript theta is set of all phi in phi, which consists of all those roots phi, which are linear combinations only of the elements in alpha and delta. In other words, M alpha is 0. Everything can be written as a linear combination of roots I told you in delta. But then I want only those which appear in theta. So M alpha is 0 if alpha is not in theta as a condition. So linear combinations of only those elements which are in theta. Those roots which are linear combinations of elements in theta, call that phi sub theta. And psi sub theta is the set of all phi in phi, which consists of all those roots which are sums of sigma M alpha alpha with M alpha greater than 0 for some alpha in delta. Note that once M alpha is greater than 0 for some alpha in delta, M beta is also greater than or equal to delta for every beta in delta. So I want to make sure that it is 0 for some alpha in theta. And then you can form the Lie algebra, which is centralized of T with these things added on, namely G phi, phi and phi theta added on. This is a Lie subalgebra, and so also is n theta, which is the sum of all the G phi as phi resource psi theta. Moreover, the corresponding subgroups Z sub theta and n sub theta are Q algebraic subgroups of G. Z theta should be Z theta normalizes n theta, and P theta, the symmetric product of Z theta n theta and n theta, is also an algebraic Q group. Such a group is called a parabolic group, and it's a parabolic subgroup corresponding to the subset theta of delta. As theta becomes larger and larger, this part Z theta becomes larger and larger because you allow more linear combinations of elements as things get larger. And similarly, then the subgroup n theta shrinks as you enlarge theta. P theta is the Q parabolic subgroup G corresponding to theta. And n theta is unipotent radical of P theta, the maximal normal unipotent subgroup of P theta. There is, in an algebraic group, there's the maximal normal unipotent subgroup, and that's called the unipotent radical. So for P theta, the unipotent radical is n theta. Perhaps I should mention that if you look at the special case of SLN, the parabolic groups are all obtained this way. You take some number of diagonal blocks, split the vector space into, split the basis, standard basis vector space into, partition it, and to that partition you will get number of diagonal blocks, and then you take all matrices above the diagonal blocks, including the diagonal blocks, that will be a parabolic group. And the corresponding sub theta, Z theta will be the diagonal blocks, the group of diagonal blocks, and n theta will be the upper triangular matrices, one in the diagonal blocks, identity in the diagonal blocks. That will be the case. That will be the, those will be the parabolic groups in the case of SLN. Lemma below has a crucial role in the proof of the main theorem. Well, I don't think I'll be able to really give a comprehensive proof of the main theorem. I will indicate something, but assuming a number of things. And one of the things I'm going to assume is this lemma. Assume that Q rank of G is greater than or equal to 1, and R rank of G is greater than or equal to 2. Set theta to be empty if Q rank G is 1, and theta to be equal to alpha if for some alpha in delta, Q rank G is greater than or equal to 2. These are things which correspond to next to minimal parabolic subgroups. Theta is a single element alpha. In that case, what happens? The parabolic subgroup will have all the unipotent radical of the parabolic subgroup will have for its Lie algebra the sum of all eigenspaces which involve alpha with some non-zero coefficient. So those roots which have alpha as a non-zero coefficient, the corresponding eigenspaces, sum them up, and that will be the subgroup unipotent radical of the parabolic group. And the centralized part will have the torus plus the rank 1 subgroup, whose Lie algebra will correspond to the roots, all roots which are multiples of alpha, both positive and negative. That will be the rank 1 group. Rank 1, that will be a rank 1 semisimple group, which will be part of the Z singleton alpha. That's the case when Q rank is greater than 2. When Q rank is 1, I'm looking simply at the minimal parabolic group. That is, this delta itself is a singleton set, and I'm looking at essentially at ZT times P. That situation. In that situation, if these assumptions are made, then there's a connected Q algebraic subgroup M in Z theta and an element T in MQ with the following properties. First, N theta as a Lie algebra is generated by all eigenvectors corresponding to all eigenvectors of add T corresponding to eigenvalues which are not equal to 1. See, add T is some element of MQ. About M, I will have more properties. Will presently come to that. I have a subgroup. I have an element T in MQ such that the Lie algebra N theta is actually generated by this set of eigenvectors of T. I only take those eigenvectors which corresponds to eigenvalues which are not equal to 1. Take that Lie algebra, take those eigenvectors and take the Lie algebra spanned by them. That will be N theta. The parabolic unipotent radical parabolic group will be that. And M itself is a subgroup of Z theta. Remember, our parabolic group P theta was Z theta times N theta. And the next important property is that if you look at B, which is the group times N theta, M is after all subgroup of Z theta, so normalizes N theta. So B is the symmetric product of M and N theta. Then B by B intersection GZ is compact. So it's a group in which GZ has a fairly big size. That's the kind of set B's. Notice that you have an element in theta in element T in MQ, which is infinite order. I'll say it has at least one eigenvalue, lambda not equal to 1, because N theta is generated by these eigenspaces. So there are eigenvalues not equal to 1. Therefore, the element theta is infinite order. And therefore, you find that the group M is not only infinite order, it's the group generated by T is a closed non-compact subgroup inside Z theta. And therefore, it's a this group M in particular is a non-compact group. And then you find that M B by B intersection GZ is compact. It also implies M by M intersection GZ is compact. I will not give the proof, which is somewhat technical.
Just a quick question. Oh, where does the hypothesis, I mean, this real rank greater than equal to 2, Q rank greater than equal to 1 come in?
Right. I'll tell you. When Q rank is greater than equal to 2, it's automatically R rank is greater than equal to 1. Okay? There's no problem there. But the situation can arise when Q rank is 1 and K rank and the R rank is greater than equal to 2. It is to take care. In that situation, see what happens is this. In that situation, what actually happens is, if you look at the centralized lift, look at the P, the minimal parabolic group, and then you look at the subgroup on which all characters defined over Q are trivial. Then that subgroup, if I call it 0P by 0P intersection gamma is compact, is a consequence of the Borel-Harishchandra theorem. You know, they had a criterion for compactness which can be applied in this situation.
Thanks. Yeah.
And that is takes care of the rank 1 case. In the rank greater than 1 case, what happens is this: you have this unipotent radical. It is also normalized. See, you have this unipotent radical is a parabolic group. It's also normalized by some other G beta. When the Q rank is greater than 2, it's also normalized by some other semisimple subgroup G beta, which is non-compact. I mean, G beta of rank 1, which is non-compact, which also normalizes this. See the, and then this, then you can find a torus inside, and and a non-compact torus inside that, which will normalize this, and then you can pick an element there which will have this property, which has the property we want. That's how, in the case when Q rank is greater than equal to 2, this is handled. In either case, you can find this element T inside Z theta. So this is essentially the consequence of the so-called Godma criterion, which tells you when G mod gamma, when G mod arithmetic group is compact. So here is what happens in the special case when G is SL3R. Pi is a standard basis, 1 to less than 3, and set V equal to RE1 plus RE2. The two-dimensional space spanned by E1, E2, and then P theta to be G in G, G3 is contained in R. That is, G stabilizes the one-dimensional space generated with third vector. So it's you take the diagonal blocks defined by the two-dimensional space E1, E2, spanned by E1, E2, and the one-dimensional space spanned by E3, you get a diagonal block, and you take all upper triangular matrices with respect to this diagonal block, including the diagonal blocks plus everything above the diagonal. Take that. That is the group P theta here, in this case. Theta corresponds to one root. Theta, as I said, is a singleton in this case because I'm working with SL3R Q rank 2. So I'm working with that. So that's the group. P theta is that group. And then, yeah. Oh, suddenly jumped to 19. What happened? My God. Yeah, it's 19 is right. Okay, I seem to have missed out something, right? Writing something. I had it written up last time, but it was not clear. So what happens is this: to get this kind of element T, you think of this two-dimensional vector space as you identify this two-dimensional, the span of Z1 plus Z2. We identified with Z1 with 1 and E2 with root 2. That becomes a Q vector space with the basis. Okay, and then you look at the group of normal elements, that is the quadratic extension Q root 2. You look at the group of normal elements. You can think of that as the points in Q root 2 tensor R, and then the norm extends to Q root 2 tensor R, and then you look at those elements with determinant 1. So you get an algebraic group over Q, which R points is a diagonalizable torus. And you can take an element which is a unit of infinite order in that. Like, for instance, you can take 2 plus, what is it? No, 3 plus 2 root 2. You look at an element like 3 plus 2 root 2, that's a unit, and that will serve as the element T. Units are going to be elements in this norm elements. 3 plus 2 root 2 is, by the way, is norm 1. And that will serve as the element T in this special case SL3R. Okay. Now, here are a few technical lemmas which I will need. By the way, I will probably more or less give a proof in the case when the Q rank is 1 and K rank is 2. That Q rank is 1 and K rank and R rank is greater than 2. The general case starts there and goes further. I do not know if I have time to cover that. And in any case, it's a complicated technical thing. Let's see if I can say something about it. Okay, here is a lemma. Suppose S is a soluble group of the form B times U of symmetric product of two, no, not soluble, sorry. S is some algebraic group, which is a symmetric product B times U, where B and U are algebraic groups, connected algebraic groups. Then there is a constant C greater than 0 and an integer P greater than 0, such that for all B in B and U in U, this inequality holds. Uh, well, I've forgotten something important here. Yeah, I would also want to assume that U, the Lie algebra of U, is generated by the eigenvectors corresponding to an element T in B, the eigenvectors of add T corresponding to eigenvalues not equal to 1. Like what I had postulated in the earlier, I want to assume that there is an element T in B with the property here, which I seem to have forgotten to mention. So there is an element T in B with the property which I mentioned in the last lemma. Now, once there is such an element, then you have this kind of inequality. 1 plus norm of BU is equal to 1 plus B norm U is equal to 1 plus norm B norm U power P for some integer P greater than 0. And of course, there should be a constant which I seem to have forgotten. Also, yeah, there should be a constant C times this anyway. Now, the first inequality is obvious because norm B, usual norm B into U is less equal to norm B norm U. So this inequality is obvious. This inequality is less obvious, but it's quite easy. The reason is the following. To prove the second, observe that the mapping BU to BU is a mapping from the group S, sorry, from B cross U, B and U are algebraic groups. I look at B times U, B times cross U into S. That mapping is an isomorphism because it's a symmetric product. We know it's an isomorphism of B cross U of affine varieties on S. Isomorphism of affine varieties of B cross U on S. And so is its inverse. Its inverse is also, and its inverse is a pair of morphisms, right? It goes from S into B and S into U. There are a pair of morphisms. Now, which I call F and H. Now, F and H are polynomials in the entries of elements of S. In the element of S, the matrix, and F is a polynomial in that entries, and H is a polynomial in the entries here. And now, if I look at, so F is at F of S, sorry, F of any element S, small s in S, is a polynomial sigma a n s power n, of that kind, okay? And then the norm clearly, if I take the highest degree, the norm will be bounded by some constant times that norm of the norm of the, yes,
Excuse me.
yes, please.
Yeah, I think in that extreme inequality, you should have norm B into U. Otherwise, it's trivial. Your P is a positive integer and the left-hand side is greater than or equal to 1.
Oh, P is a positive integer. So
yeah, that's what.
So this will be, what's the problem? Being greater than 1, how does it matter?
No. So this and then the right-hand inequality is trivial. I mean, X is always.
I told you, sorry, I told you that there should be
norm B into U.
There should be a constant C.
Norm B into U.
Sorry, I missed out a constant capital C here. And in any case, I'm interested in this only when B and U, norm B and norm U are large. Okay,
no,
maybe.
Why do you have to put a constant? Your left.
Yeah. I said there should be a constant. I postulated a constant C, but have not used it here. So the constant.
No, I think it's basically what Josina is saying is that you have this quantity which is greater than equal to 1.
To 1. So 1 power P.
So X is less than equal to X power P.
Yeah.
Sorry.
You have X greater than or equal to 1. X is.
P should be an integer. There's an integer P greater than 0.
Yeah, that's what I'm saying. So like X is always greater than or equal to X power N, right? Whenever X is greater than or equal to 1, that's completely trivial. Norm B.
Sorry. I'm sorry. This should be norm B times U. Sorry. It should come in.
Norm of B times U. That's
yeah. Sorry. I've written it down wrongly. Norm of B times U. And the reason of course is that B times U, norm of U, B times U is a polynomial in the entries.
Yeah, that is fine. That is
and the entries of U. And therefore you get bound by the degree of the polynomial, which is called P. Sorry.
And then you need that constant C.
I need the constant C and B times U is needed. Yeah. So, I'm sorry, it's this typing, I always make many errors and I don't correct them properly. Anyway, All right. The second inequality follows readily from the fact that this norm of B times U is B times U is a polynomial in the entries of B and U. Okay. Now, let U be a uniform group and B in G a semisimple element, normalizing U, and B the, here I don't really need the condition, extra condition which I put in this. Proof is straightforward. I'm sorry. I don't think I need a bother. I'm only making a statement about norms, and all that you need here is that it's a symmetric product. I don't need that extra element T in B. The extra element T in B has a role in the next lemma. So next lemma says if U is a uniform group and B in G, a semisimple element normalizing U, and B the Zariski closure of the cyclic group generated by Zariski closure is a cyclic group generated by B. It's an algebraic group. I'm sorry. Okay. Suppose that the Lie algebra U is generated by the eigenvectors of at B of real eigenvalues not equal to 1. Then restricted to S, the distance function of G restricted to S, same as distance function of S on BU. The point is this. This is, as far as S is concerned, dg restricted to S is same as ds restricted to S. Sorry, as far as B is concerned, dg restricted to B is same as ds restricted to B, because B, after conjugation, can be made into diagonal matrices inside R over the real field, and then it becomes totally geodesic in G. Therefore, for B, there is no problem. Even it's totally geodesic in SL and R. So in B, for B, there's no problem. It's only for S, for U, there's a problem, but that is taken care of by this T business. So in view of the lemma, suffices to show that dg restricted to B, so here it should be equivalent, is equivalent to ds restricted to B, and dg restricted to U is equivalent to ds restricted to, not equality, but equivalent. For B this follows, for B this follows because B has a conjugate which is totally geodesic in G. It's difficult to see that the statement for U can be deduced from the special case when U is exponential txt in R with x in n, an eigenvector for a real eigenvalue lambda greater than 1. This follows from the fact, and here it follows from the fact, exponential lambda rx is b power r, x power x, b power minus r. So by the triangle inequality, the distance of this element lambda power x, exponential of lambda power x, is the distance of b power r from the identity times distance of x from the identity times b power minus r from the identity. This b power r has a distance of r from the identity, and this b power minus r also has distance of r. So if you look at this whole thing, this distance is 2r, which is r times log lambda, and x being nilpotent, lambda power rx is a polynomial in lambda power r, and from that it follows what we want follows. So the distance in basically it says the distance in S restricted to U behaves again like the norm. So that now, so this is a case when U is actually generated by exponential of an eigenvector, exponential tx, the one parameter group of an eigenvector. But the general case, we're assuming it's generated. Once again, it's not difficult to see this. I will not go to the proof. It's a little technical, but one you can work it out quite easily. The point is that those elements, any element is essentially any element which is not one of these, which does not correspond, because I'm assuming it's generated by these eigenvectors. You can see that any element in U, it's if it's not an eigenvector, it's a product of these elements coming from these one parameter groups of good eigenvectors times commutators among them. So from that, it is quite easy to deduce that the statement is proved more generally. So it follows that dg, distance function of g restricted to uz, is ellipsis equivalent to ds restricted to uz. So, and since dg restricted to z is c times dgz is less than c times dgz, you find dgz uz is less than dsz. We conclude that lgz u power r equal to o ln r, logarithm of r. See, this is one of the things I stated. If you remember, for a unipotent element, if the way the word length increases, it's like the logarithm of the sorry, if the word length in LGZ increases like the norm of the element u power r as r goes to infinity. So this follows for now for elements in uz. So in particular, this will follow for elements in the unipotent radical of a parabolic group corresponding to a single root alpha in a higher rank group, or in the case of in the groups of q rank greater than or equal to 2, and in the case of q rank 1 for the unipotent radical is the unique of the unique parabolic group over q which it has.
So this particular one does not use your technical lemma where you had this condition of q rank greater than or equal to 2, q rank greater than or equal to 1, r rank greater than or equal to 2, right?
No,
this is true.
It uses the existence of the element t because I want.
Oh, I see.
That u has the property, to conclude that. So I need it. The technical lemma is needed for this. Basically, is I'm just isolating the thing you need to apply to that special case when it's a unipotent radical of a parabolic group. Then here is a corollary. If G is of rank greater than 1 and R rank greater than 2, then D. Sorry. Then DGZ, the word metric on GZ. So this, sorry, Z should have been here. DGZ restricted to UZ is equal to DG restricted to UZ. DG restricted to UZ is essentially norm metric. Now, why is this true? We saw that it's true for the unipotent radical of a parabolic group corresponding to rank 1, corresponding to 1 root alpha. It's going to be true for every such root if the rank is greater than q rank is greater than 2. It's going to be true for every such group, and then you can put these together because you can write the maximal unipotent group, maximal unipotent Q group as a successive symmetric product of subgroups, each of which sits inside some parabolic group corresponding to some root alpha. So if you do that, then we can apply the theorem we said about symmetric products and conclude that this is true. And now it turns out that every element, every unipotent element in UQ has a conjugate. Let me first. I stated this some time ago, but not in this form. But following is a statement. It turns out that if you take look at the set of all maximal unipotent Q subgroups, all maximal unipotent Q subgroups, these are unipotent radicals of minimal parabolic subgroups. This set up to conjugacy by elements of GQ is finite. So you find that there are only finitely many gamma conjugacy classes of maximal unipotent groups. And for any one maximal unipotent group, this property of this is true. And since there are only finitely many conjugacy classes of elements, so it's enough to check that this is true for finitely many maximal unipotent subgroups. And then for that we have checked it for one maximal unipotent group, and for finitely many, obviously it follows. So from that you see that the word length grows for a unipotent element. Every unipotent element which is Q rational, that is a Q point of G, which is unipotent, has a conjugate in UQ. And if it's integral, it has a conjugate in some UZ among a finite number. So we see that we have proved that the statement that LG U power R is O log n R for all unipotent elements in the integral points of GZ, provided Q rank G is greater than or equal to 2, or Q rank G equals 1 and R rank G greater than or equal to 2. We want R rank G equal to greater than or equal to 2 is the condition. That's a condition we needed for applying Margulis theorem to begin with. Now, fix a Q simple group of Q rank greater than 1 and R rank greater than 2. We also fix a maximal. Now, what I want to do is I want to deal with the special case when G is of Q rank 1 and R rank greater than 2, where I want to prove the theorem that the word length metric is Lipschitz equivalent to the metric coming from G from the ambient group. In the special case, I want to prove the statement. Towards that, so we fix a Q simple group. So from now on, I'm going to look at a Q rank 1 group, but sometimes this Q rank 1 group may be sitting inside a bigger group of rank greater than 2, which is for which I use notation G. But now the ambient group may be Q rank greater than 2 H. So Q rank greater than 2, but the group I'm interested in is one of the G alphas there, which is a Q rank 1 group. And so strictly speaking, the way I should have put it is Q is a simple Q is a Q simple group of G rank 1. Let me say first, this is the situation in which I'll prove the theorem first, the main theorem towards that end. If this is true, then the main theorem in this special case reads like this. It's little, I'm sorry, it's a simple. Okay, let me state the theorem I want to prove. Let alpha and delta and G alpha be the Q rank 1 subgroup corresponding to alpha. This means, remember I defined this subgroup G alpha as a symmetric product of what I called this one corresponds to P subscript singleton alpha. P theta I defined for any parabolic group. And look at P alpha have 2 parts, Z alpha and U alpha. And this is the more or less a semisimple part of Z alpha. That's what this is, G alpha. G alpha be the Q rank 1 subgroup corresponding to alpha. Then the metric on G restricted to G alpha Z is equal to DG alpha Z, DG alpha restricted to DG alpha Z, which is same thing as DG alpha Z. You see, G is the bigger space and G alpha is the rank 1 group. And I'm assuming that the capital G, the G has Q rank greater than or equal to 1 and R rank greater than or equal to 2. We fix a maximal Q split torus and a simple root system, etc. as above. Then this is a statement for alpha and delta, G alpha be the Q rank 1 subgroup corresponding to alpha. Then you look at the distance function on G restricted to G alpha Z, the integral matrix in G alpha, that is equivalent to DG alpha restricted to G alpha Z, and that in turn is equivalent to DG alpha Z. That is, this is the word metric on G alpha Z. Sorry, this is not correct. This should be G here, DGZ. Right, should be DGZ, not DG alpha Z. Because we've seen that if it's a purely Q rank 1 group like SL2Z, SL2R, SL2Z and SL2R, this won't be true. So this should have been, I should have written DGZ, G, not G alpha. Okay. See, DG alpha is not restricted to G alpha Z, is not in the case of G equal to SL2, for instance, G alpha equal to SL2, for instance, is not true. So this should have been G alpha, sorry, the word metric on DGZ, GZ as Q rank 1 and R rank greater than or equal to 2. For the proof of the theorem, we need a description of a fundamental domain for GZ in G for the right translation action. This description is given by Borel, and I have to introduce some additional notation for this. So let sigma be a finite set of GQ which maps bijectively onto this double poset space. GQ, P phi Q. This is the minimal Q parabolic subgroup P phi, and I take Q points of that. GQ by PQ, take the quotient set, and then pass the quotient further by gamma Z. this set turns out to be finite. That's part of Borel's theorem.
So this is the set of cusps, is it essentially in the quotient terms?
This, if you like, is called the set of cusps. Yes, exactly. Let A be the identity connected component of T as the maximal split torus, Q split torus. For C greater than 0, AC is a set of all T such that alpha T is less than C for every alpha in delta. It's the kind of thing that if the Q rank was 1, it's just T is a, if you think of it as a straight line, think of it as R plus, which means 0, everything greater than 0, and then it's in some sense 0 is not within the finite, it's not in the finite part. Torus is 0 less than T less than infinity. That's the torus, and that's a group A. And you look at the set of T in A such that alpha T is less than C. So you cut off at some point and look at all elements T such that T is less than C. You think of alpha, the character alpha as a homomorphism into R plus, which is, you can assume, is bijective because we are working with over real numbers. Alpha is certainly 1 to 1 on on the part on the connected component. There's no problem. So I want to look at this set AC, which is if you think of the upper half plane and the usual fundamental domain of the modular group, this AC, when it's kind of reverse directions, one goes everything above a certain point. If you like, I've instead of looking at this, I could have looked at T such that alpha T inverse is less than C. That would mean T goes beyond a certain point. So that's the, so in the, basically what I want to, this A corresponds to the vertical line in the case of the modular group in the fundamental domain, and you will see presently how it connects up. And for 0 less than C prime less than C, A C C prime alpha and a root alpha in delta consists of all those T in AC, which means alpha T is less than C, but every beta T is less than C for every beta in delta, but for this particular alpha, you want alpha to be even lower, alpha T to be less than C prime. So in the case of rank 1, it's everything below a certain C prime, between 0 and C prime, where C prime is less than C. We fix a maximal compact subgroup KFG, and P phi is the minimal parabolic group, and set P phi equal to P. I've forgotten to put that there. P phi equal to P so that Kp is G. This is the so-called Iwasawa decomposition. In fact, P itself has a further decomposition, and there is a compact part in P which you can absorb in this K. That compact part is already in K, so that can be absorbed in here. But nevertheless, it's not a it's not, unlike in the case of the Iwasawa decomposition, it's not a product. There's the intersection K intersection P will be a maximal compact subgroup of P, in fact. So K times P is G. And let me denote by 0P the set of all X in P, such that chi X equals 1 for every chi in XQP. For every character chi on P, which is defined over Q. The notation XQP is for characters which are defined over Q. That is, those are homomorphisms of P, which is a Q subgroup, into R star, which are given by polynomials in the entries of matrices in P. That character should be, it's a function into R, and it's a function into R cross, and therefore into R, and that should be a polynomial with coefficients in R, with coefficients in Q. That's the condition for a character to be defined over Q. And chi X equals 1 for every chi in XQP. Then 0P by 0PZ is compact. This is, as I've already mentioned, the consequence of so-called Godma criterion. And this is what helps when the Q rank is 1 and R rank is greater to 2, what happens is that the 0P has a large infinite subgroup, non-compact subgroup sitting in it. Large because 0P with 0PZ is going to be compact. 0P is, there's a part 0P which sits inside the centralizer of T, and a part which is unipoint radical. Inside the centralizer of T, there is a big subgroup of P, non-compact subgroup of P, whose intersection with gamma is a co-compact lattice, that non-compact group. Okay, with this, I can say let omega be a compact set in 0p such that omega psi inverse. Recall that this psi is a set of representatives in the double coset class GQ by PQ by gamma, set of cusps. And what I want is that omega should be a compact set such that the following thing happens. You look at psi inverse GZ psi, the conjugate of GZ by psi, and intersect with 0p. I should have, sorry, it should be psi inverse. I put things in wrongly, I think. Anyway, psi inverse GZ psi, intersection 0, maybe it's okay. I look at this conjugate of GZ, intersect with 0p. This times omega times this should be the whole of 0p. In other words, I can look at this intersection with p. That should, see, I wanted, we know that there is a compact set such that omega times this is compact because this is a co-compact lattice inside 0p, this intersection. Because psi is an element of GQ, remember? So, and this is true for every psi. For each psi, I can choose omega psi, but then I can take the union of all those and make sure that this is true for every psi, in capital psi. Then there is a constant c greater than 0, such that if I denote by omega c, this set, union of SC omega psi times this omega c times GZ is G. And what is this SC omega psi? S is, this is Gothic capital S. SC omega, what is the definition of this? This is a set K times AC times omega. The whole of G is Kp. And now I look at those points of Kc which look like K times A times U, where A is in AC. AC, remember those which are below a certain level in the cone, which is given by the characters. So alpha is this set of all elements A, such that alpha A is less than C for every A, for every alpha in delta. That is AC. And this is a part of the part of A, which is the product of R stars. And the product of R stars, and then this, notice that this is a closed, it's a non-compact set. It's a non-relatively compact set. There are elements in it which go towards infinity, towards the element 1. I should say element 1. They go towards C goes to C. They go towards 0. C goes towards 0. So this element, this torus itself is like the product of R plus several copies, and elements can go to infinity by some component going to 0. So, and then this is of course the compact set. I look at AC omega is K times AC times omega. Such a set, in fact, is called a Ziegel set. What we have said here is that there is a finite union of translates of the Ziegel set, which forms a fundamental domain for GZ. That is, GZ times this set is all of G. This is obviously a non-compact set, so the lattice is not uniform. The moment rank is greater than Q rank is greater than 1, it's not going to be uniform lattice. Further, if B is any compact subset of G, the set of gamma in GZ such that omega gamma intersection B omega is not empty, is finite. See, in particular, this means omega gamma intersection omega, this set of gamma set omega gamma intersection omega is not empty, is finite. In other words, this omega C has finitely many neighbors under gamma. But I want to say something stronger. I can plug in a compact set and look at B times omega. Instead of omega, I can look at B times omega, which enlarges omega. But remember that now B itself can be written as K, KT, KAN, every element of B can be written as a product, and these are all bounded things. And then by you have KAN times K prime, A prime, N prime, element here and element here. And then you can rework right in the Iwasawa decomposition. And then you find what you get is some, again, it will be K times A times AC will be enlarged So it will get into some AC prime. And AC may get enlarged, so it will get to some AC prime. And omega may also get enlarged, so it will become some omega prime. So it's again a set of the form, a number of translates of the Ziegel set. Ziegel set is a set of this form. Is some C greater than 0 and some omega compact. So this is again a finite union of Ziegel sets. What this says is that if you take any two finite unions of Ziegel sets, then the translates of one gamma, those gamma which translate one to intersect the other is a finite set. Also, here is a extra statement which is needed for us. Given this B is given to us, suppose once this B is given to us, then there is a C prime in C such that the following holds. If gamma is in PZ and omega C SCC prime alpha omega, remember I define this CC prime alpha omega as a set of all K A U, K in K, A in A, and U in omega with the property that A alpha beta A is less than to C for every beta and delta, but alpha A I want to be even less than C prime. If that happens, so this Ziegel, this finite number of translated Ziegel set, and then the set I'm looking at is a smaller one. Omega C intersection. Oh, sorry. I got it wrong here. It should be omega C prime here. First one should be C prime. And SCC prime alpha omega dot psi. If this intersection is not empty, in fact, sorry, I've got this wrong here. What I want is this, sorry, it should be both be omega C and this omega C, so this C prime there. What I want is omega C intersection. This should be omega C prime, not SCC prime alpha omega, but omega C prime. Suppose omega C intersection omega C prime psi is not empty, then gamma actually belongs to the parabolic subgroup. This parabolic subgroup psi inverse. So I'm assuming that translate by psi of this Ziegel domain, which should be SC prime omega. This should be, sorry about this. This should be SC prime omega. If SC prime omega psi intersect omega psi, I also seem to have forgotten a gamma in here. So omega C times gamma intersects omega C prime psi. If this intersection is non-empty, then gamma actually belongs to psi inverse P delta minus alpha psi. I get the parabolic which corresponds to delta minus alpha, a maximal parabolic if you like. So in any case, this notation of course is correct, but it's irrelevant for us. Here it should have been, as I said, omega C prime times psi. That intersection is not omega C gamma intersection. Omega C times gamma intersection omega C prime psi is not empty. Then omega C of course contains all the translates of Ziegel domain. Here I'm picking one particular Ziegel domain corresponding to psi, some translate to the Ziegel domain. Then I can say the following theorem. For alpha and delta, dg restricted to g alpha z is equal to dg z intersected restricted to g alpha z. Okay. In particular, it will follow that if G itself is of K rank 1 and R rank greater than equal to 2, then I could have replaced this G alpha here as well, this G alpha Z by GZ here. Both these G alphas could have been replaced by GZ if G alpha equals G. If the rank 1 group is already G. Now, the crucial fact we have already available under our hypothesis that capital G is of R rank greater than equal to 2 is this dg restricted to 0 pz is equal to dgz restricted to 0 pz. In particular, we follow that it is dg restricted to pz 0p alpha z. If you take the parabolic inside g alpha, dg inside p alpha z restricted to 0 p alpha z is same as dg restricted to 0 p z. Now, the J alpha is Q rank 1 subgroup determined by alpha. From now, I will now set G alpha equal to G and adopt all the notation introduced in the connection. In other words, G itself is going to be a Q rank 1 group, but at the back of our mind, we are always aware that G we are treating, G we are looking at is a subgroup in a big in an ambient group of R rank greater than equal to 2. The R rank of the ambient group is at least 2. The Q rank may be greater than 1, maybe 1. So that is at the back of our mind. But to avoid cumbersome notation, I want to rework the notation and simply take G alpha to be G and use all the notation introduced so far for G. In particular, dimension T equal to 1 and delta reduces to the singleton alpha. Also, since Q rank G is greater than or equal to 1, that GEQ is okay, tech. Okay, Q rank G greater than or equal to 1, we have for 0 less than C prime less than C, AC minus A, C prime, this should be suffix C prime, AC minus AC prime is compact. Remember, you have this line R plus is the thing, and those which are below C, and then I remove from them those which are below C prime, so everything is caught between C prime and C. And that's compact. Well, it's not quite compact. Its closure is compact. It's relatively compact because AC itself, AC is a non-compact set, and by removing A, I don't land in a compact set. So this is a relatively compact set. But I'll probably keep on saying AC means AC prime is compact. That will not matter. You have to always take it as meaning the closure is compact. So also is omega C minus omega C prime, because after all it's K AC times omega. K and omega are compact sets. Only the AC, there can be infiniteness non-compactness only inside AC, and AC minus AC prime is relatively compact. So we also have the following fact in this special case. I'm just writing this. This is a main theorem I'm essentially restating. Given rho greater than 0, there is a C prime equal to C prime C rho, such that the following holds. If xy is in C omega, with dg xy, dg xi, y eta, xi is a point in the fundamental domain, y eta is also a point in the fundamental domain, less than or equal to rho. I'm fixing a rho. Suppose this distance is less than or equal to rho, and xi gamma equals y times eta. That is the translate by gamma of xi is equal to y of eta. Then the crucial thing is disappeared. It's gone below. It just says that then what happens is then this element gamma is in the parabolic group, minimal parabolic group corresponding to psi. Then the element gamma, which I have xi gamma, if in other words, if gamma translates a point in the Ziegel domain, in the one translative Ziegel domain into a point in the another translative Ziegel domain, which is fairly low down, in the sense that the element of the total part of the product is gets closer and closer to 0. If it's sufficiently close to 0, then this gamma should belong to the parabolic corresponding to psi. Notice that I have psi and eta here, but it turns out that eta has to be equal to psi, and you find that gamma belongs to psi inverse P0 psi. That's the statement. I'm sorry, it has disappeared into the portion which is not visible. Okay. Okay, now let me write Gz equal to gamma. This is to make notations. I will also assume that GQ by gamma by PQ is a singleton set. This is not a, this assumption need not bother you. Of course, it doesn't generally hold, but you will see that the proof as we give it can be modified very easily to take care of the general case. So this can be carried over with minor changes. With the change notation, we have to keep in mind that G is a Q rank 1 subgroup of a Q group of R rank greater than 2. Because of this, we have already something about the group DGPZ. This is the distance function related to PZ is equal to logarithm of the norm. This we have seen because of the fact that it's a subgroup of the R rank 2 group. And this is the crucial fact which we will need later. This one crucial point input that is needed. Fix rho greater than 0 and C prime be as the theorem. The C prime is the one which determines how a gamma and when a gamma is forced into a parabolic subgroup. A gamma which takes a Ziegel set into to translate Ziegel set to intersect with it again, non-trivially, then that kind of thing is determined by the C prime. Let A be the diameter of omega C minus omega prime, and B equal to max rho B. Rho is something which you fix, remember, in the theorem. That's the one which determines how elements get into parabolics. Now, let F D0 G gamma to G is missing here be a geodesic path in G, parameters by arc length joining 1 and gamma. DG gamma is the distance of gamma from G. So the metric on G is complete. It's a complete Riemannian metric. So there is always a geodesic, minimizing geodesic joining into points. So there is a path from 0 to DG gamma, which is a geodesic path, and it's a parameter by arc length joining 1 and gamma. Let n equals to DG, and so I want to split this path up into n equal portions where n is DG by rho. Each portion will be of length r. And for 1 less than to I less than to n, Ti will be I rho plus epsilon, where epsilon is the remainder after dividing by rho. Integral. This is the integral part of the of dg by rho. And then there's something left which is epsilon, which I call epsilon, and you have this kind of thing here. Okay. So FTI is GI. GI are elements on the path, and the distance from GI and GI plus 1 will be exactly equal to rho, except the first one from identity 2 to G0 is identity, which is 1. From G0 to G1, that is of distance epsilon. The rest of them is for subsequent, for consecutive points, the rest of them, difference between consecutive points is precisely rho. Let xi be in omega c and gamma in gamma be such that xi gi equals gi. This is after all a fundamental domain. So there are the gamma I which will take this gi. Oh, this should be gamma I. Gi should be gamma I. Xi gamma I equals gi. Write theta 1 equal to gamma 1, and for I greater than 1, theta I to be equal to gi plus J plus, sorry, this should be again gamma I plus 1. Gamma I plus 1 times gamma I inverse, so that gi plus 1 becomes gi theta I. This is just 2. This definition of theta I is made so that this is true. Gi plus 1 equals theta, gi theta I. So the distance between gi and gi theta I is going to be rho, remember. Gi theta I is after all gi plus 1. The distance from gi plus 1 is rho. So gi theta I to gi plus 1 is rho. Let C prime be as in the theorem. That's the one which determines when an element gamma taking a point in the Ziegel domain into itself or into a slightly different Ziegel domain belongs to a parabolic group. Define the increasing sequence integers as follows. If you look at this xi are all in the Ziegel domain. Okay. So I look at those points gi where the element, the corresponding element xi belongs to this compact set, a relatively compact set. So I look at those LR are elements, the LR are among the elements 1 to n of I, among the I's. So LR are defined as follows. So YR should be some XLR YR should be equal to XLR with XLR belong to this compact set. So when you go along, some of the GIs you translate by gamma I will go into the Ziegler domain, of course, but some of them may go into the compact set, some of them will not. So those which go into the compact set, I take them in order of increasing order of R, call that YR to be XLR. There will be some points Li, LR 1 less than to R less than to something, such that XLR will belong to this compact set. I write them in increasing order. And then how do I determine which are the points which I call LR? That is, in between LR and LR plus 1, these points get outside of, they get into omega C prime. They're outside omega C minus omega C prime. So, while Xi is an omega C prime for I between LR and LR plus 1. Then from the theorem, one sees that LR plus 1 minus LR is, if LR plus 1 minus LR is greater than or equal to 2, then theta I is in P. So if LR plus 1 minus LR plus, and you take any 2 points in between, those 2 points are that transforms into the Ziegler domain are inside omega C prime. And our definition of C prime ensures that theta I will be in the parabolic group. In fact, it's enough that, for 2 elements in the parabolic group, if one of them is an omega C prime, the other may be anywhere in omega C. And if the conjugate, if the gamma translator that meets omega C, then that element gamma should be in the parabolic group. That is what the criterion defining C prime was. Then from the theorem, one sees that this theta I for I between LR plus 1 and LR all lie inside P. And therefore, the product also lies in P, which I call nu R. This product is in P. Now, dg of 1 gamma can be written as the sum 1 less than to R less than to G gamma of distance between Gi and Gi plus 1. GLR and JLR plus 1, which is missing. GLR to GLR plus 1. That's after all, the geodesic passes through GLR and JLR plus 1. And therefore, the sum GLR plus 1 is what you get there. So, I know that we know the statement for the parabolic group that the dg is ellipsis equivalent to d sorry, we know that by the definition of the geodesic, the dg 1 gamma is a sum of these dg gamma rho. Sorry, dg gamma big rho from 1 less than to R, which from GLR to GLR plus 1. Okay, GLR to GLR plus 1. GLR plus 1. So there is a constant k greater than 0 such that dg nu R, this nu R is the product, dg nu R is greater than 2 constant times L nu R. Because it's the parabolic group, and for the parabolic group, we have already stated that the statement is true, that the intersection of dg, sorry, the restriction of dg, d capital G, is ellipsis equivalent to the length, the metric given by the length of the ambient group G intersection G, of the ambient group GZ. I have not given a name, but now I have shifted the name G to this Rankman subgroup, so that's why I write L for the length of the length in the lattice of the ambient group R rank greater than 2, of R rank greater than 2. Okay, when LR plus 1 minus LR, nu R belongs to the finite set of gamma and gamma such that B omega C union omega C. What do I have here? Sorry.
Something like G omega sub, yeah, B dot omega C, right? That's omega
B
sub C.
Omega sub C. It's not even omega sub C. It should have been
some G dot omega. Yeah.
Omega C minus C prime. It should be omega C minus C prime intersection omega C not equal to empty. and that's a fine. Anyway, okay. In any case, this is true. If in LR is equal to LR, gamma belongs to this set. Omega C intersection B times omega C intersection omega C, which is not empty. Not union, should be cap but not cup. Okay. B times omega subscript C intersection omega subscript C is not empty. and that's a finite set, and there's a constant b greater than 0, such that L nu r less than or equal to b times dg nu r. Because all these nu r's belong to this finite set. When they are consecutive, LR plus 1 LR consecutive, you will see that this is going to be true, and so it will be easily seen that this is true. Okay, so in either case, therefore, and there are only finitely many elements. Set FTI equals, oh, this is all over again somewhere in typing of, yeah, let me get here. Now, dg1 gamma is the sum of this. There's a constant a greater than 0, such that dg nu r is greater than a nu r. And this a nu r, this is the what I've just now said, and it's true because for the parabolic group, we proved this statement, or at least stated the statement in the ambient group. Okay, now, oh.
What is nu r?
Nu r is the product of the theta between LR and LR plus 1.
Oh,
Okay. The product of theta is. See,
oh, so there is another additional nu r, so that is not required.
Sorry?
So you are saying product I greater than or equal to LR less than LR, theta is in P, right?
Is in P, right? And therefore I know.
What is the nu r in the left of that?
Nu r equals the product.
Nu r equals, okay.
Yeah, sorry. That ensures that, you are looking at, so from that to sign to nu r is the parabolic group, therefore dg nu r is equal to 8 times.
Yeah, fine.
Okay. Now,
yeah.
If I set gamma to be this set, gamma b omega sub c, intersection omega sub c not empty, then there's a constant b greater than 0, such that L nu r is equal to b times dg nu r. It's only a finite set, so there's no problem about finding this. And then when I add up this, I find that what I get is on the one hand the distance, and that is going to be less than or equal to the sum of the b L nu r. So that's going to be greater than or equal to sum of the L nu r's, which in turn is greater than the length of gamma. Okay, so that will prove the theorem. I've not been very careful here about there's a little subtlety here involved, which unfortunately I've run out of time. In any case, I don't want to go into it now. There's a little subtlety involved, but you can work it out if you are careful. Of course, you can always refer to our paper in the IHS. Now that will take care of rank 1 groups. Now the general case is proved by some kind of induction. What one does is to start with the element gamma, then by multiplying gamma by elements from a finite set, you can assume that gamma has the form gamma has the form, let me put it like this, u times small p, where p is in the minimal parabolic and u is the unipotent radical of the opposite parabolic. See, if you look at u minus, which is the opposite thing, this is like the lower triangular matrices, and u is the upper triangular matrices, and by u minus I take lower triangular matrices. In SLNR, for instance, you take u minus times all the entire soluble group of upper triangular matrices, u minus p, that's a Zarichi open set in SLNR, and therefore finite many translates by gamma. I mean, gamma is Zariski dense, and so finite many translates by gamma of this Zariski open set will cover the whole of G. So that shows that by using translation by one of a finite set of elements in GZ in gamma, one can assume that the element gamma is of the form u minus times p, where u minus and p are going to be elements in GQ. They are not integral elements, u minus into p. And now, what happens is this: if you look at p, you can associate with the element gamma a certain function f gamma, which takes actually integral values. Basically, in the case of SLN, for instance, you take the standard basis and take the first vector. So what you do is look at f gamma of E1. F gamma is defined as the inner product of gamma E1 and E1 itself, the point gamma E1 and E1. Okay, obviously that's going to be an integer when gamma is the integral matrix. So you have this f gamma. On the other hand, you know that u minus divided by u minus intersection gamma is compact. So there is some element theta. Sorry, there is we know that there's a compact set omega such that u minus gamma omega is the whole of u minus. And so what I define another function which I call, let's say, what's the name? H gamma as the, it is not a function with values in integers, it's a function with values in u minus intersection gamma. I take it as an element, H gamma is some element in gamma, which transforms the original gamma was written as u minus into p. H of gamma is some element in u minus, which transforms this element u minus into the compact fundamental domain for u minus. Now, then one uses an induction, a double induction, if you like, on this function, which I called h gamma, the other function which is called f gamma. F gamma is an integer valued function, but delta gamma is a u gamma valued function. And, or if you like, you can use norm u gamma, which will also be an integer. If I take the norm to be the sup norm, it will be also an integer. So what I do is to argue by double induction on this pair of integers, f gamma and u gamma. So one forces, first of all, to start with element gamma by modifying by a finite number of elements, one forces it into the open set u minus times p. And then one again carefully manipulates by multiplication on the left by elements, suitable elements in gamma. First, reducing the function h gamma. In fact, one can reduce h gamma to 1 very quickly. And then you have to argue by induction on f gamma. Now, f gamma can also be reduced by using certain elements, carefully chosen elements. What you do is write, even the first case, write gamma as gamma theta times theta inverse. And then you analyze separately gamma theta and theta inverse. Gamma theta will have lower value for h, and therefore gamma theta by induction hypothesis will have the necessary property. The length function will be dominated by the norm function, and theta being in u minus, for which we know the statement, is also dominant, so you will get the same thing. And you have to do something similar for writing even in the case when you have to manipulate with f gamma. It's a little more complicated. You have to multiply by some element such that again you reduce f gamma without disturbing delta gamma. So if you do that, you will get a double induction, and you are writing again the element gamma as theta times theta inverse gamma, and then theta inverse gamma is lower f gamma without with the fixed delta, and therefore by induction hypothesis that's taken care of, and the element theta has been carefully chosen to have the necessary property. So using these things, you can finally prove the theorem. It's somewhat complicated, and I certainly don't have the time. And I thank you for your attention. And I stop here. I hope I got something across. I'm not too sure that I did a reasonable job. Anyway, there it is. Thank you.
Let's thank Professor Raghunathan for a lovely talk. In fact, a series of 2 lovely talks. Are there any questions?
Yeah, I just have a sort of try to sort of organize all the stuff in my head. So first, in the Q rank 1 real rank greater than equal to 2 case, first the first step that you're doing is you're proving essentially that if you chop off the cusp and you look at the boundary in the fundamental say of the quotient of the fundamental domain, then that is not distorted. I mean, on the boundary, right? One, and the second part, because it's Q rank 1, in some sense you can separate the cusps. So separate, say, the horoball. So you are decomposing your path.
In the case of Q rank 1, you cannot separate the cusps. Yeah, that's right.
No, if it's Q rank 1, no.
In the case of Q rank greater than 1, correct. Greater than 1, you
Greater
can't.
than 1, you can't separate. No, so
Right.
I'm saying the Q
Q rank 1,
rank
you can
case.
separate the cusps. Yeah.
Yeah, so Q rank 1, you can separate the cusps. So you decompose your path into pieces that go along cusps and stuff
Right.
that goes into the compact bit.
Right.
So you're
right.
estimating the first one using the first lemma, and then the rest of it is essentially in the compact part. So the length is comparable to the.
Right.
Is that a sort of a cartoon picture of?
That is a good summary of the argument, right?
Okay. Okay.
That is the crux of the argument. I didn't put it like that. Thanks for clarifying it.
Okay. Thanks.
What are some applications of this theorem?
I don't know. There's nothing. You see, it's well.
Does it have any application in automorphic forms?
Not that I know of. Not that I know of. But
Actually, there's been some recent application in this work on Zimmer's conjecture by.
what is
Conjecture?
which is
So there's this program of Zimmer on rigidity.
Zimmer
Zimmer.
Zimmer has some infinitely many conjectures. Many of them, in my opinion, don't deserve the name of conjectures. But anyway, but which one are you talking about?
No, so there's been some so this work.
This is about action on on manifolds.
Yeah,
So
smooth actions on manifolds. So,
Okay.
yeah, exactly.
So you don't have any action in low dimensions. That's the kind of thing.
Yeah, so
So
if
for
you take
example,
like
if you
action
below
on a
the-
circle of lattices acting in the circle, things like that.
Right. Okay.
Yeah, so actually there's this quite noteworthy recent work of Rodriguez, Hertz, and Brown and Fisher, where they settle some. So Zimmer had some body of conjectures about this, and yeah, so this result of Blavatsky, Moses, Raghunathan is somehow key ingredient.
Well, I mean, we looked at it simply because we found it fascinating. See,
Right.
which is probably the best excuse to do any mathematics, whatever. And, it's and of course the additional incentive was that it was conjectured by Krishna. And when someone like Krishna makes a conjecture, one takes it seriously. So, and what is more, the conjecture of Krishna and supported by Gromov, and Gromov has the right kind of intuition in geometric group theory. So one has to believe if you think something is true, one should be able to prove it.
Indeed. Thanks. So are there any other questions or remarks? If not, let's thank Professor Raghunathan again for these lovely talks.